everybody, this is Wallace from A3Academy, and today's video is going to be on thermal expansion. So let's get started. So you know when you heat up an object, that object is going to expand, and when you cool down an object, the object is going to contract. There are different formulas that you can use to model how much an object will expand or contract given the temperature. Now, the first way you can think of thermal expansion is in terms of linear distances, or linear expansion. And we can really only use linear expansion for solids because liquids and gases can change distances and change their shapes, whereas solids can't really change shape. So suppose you had an object and you measured, say, the length of the object, and you call that L0. Then you allowed the object to expand under thermal expansion, and the object increased in temperature by delta T degrees. Then you measured that same distance and called it L. There is a mathematical relationship between L0, delta T, and L. And here it is. L is equal to L0 times 1 plus alpha delta T, where L is the final length of the object, L0 is the initial length of the object, and delta T is the temperature change of the object, and alpha is the linear expansion coefficient. Now, the linear expansion coefficient of a material can change depending on the material. In general terms, a smaller coefficient means that the material will expand less when you heat it up. A larger coefficient means that the object will expand more when you heat it up. A negative coefficient is rare, but it means that an object can contract when you heat it up. For example, pure silicon will actually contract when you increase the temperature. And a zero coefficient means that the object will do nothing. It'll neither expand nor contract. Invar, which is an alloy between nickel and iron, will actually not expand or contract when you heat it up because its linear expansion coefficient is so close to zero. Here are some sample linear expansion coefficients for selected materials. Now, there is another way you can look at thermal expansion, and that is in terms of volume. And with volume, you can really talk about solids, liquids, and gases. And when we're talking about volume expansion, we always need to make sure that the environment is at constant pressure, or else none of the formulas will work. Now, the equation for volumetric thermal expansion is as follows. Delta V is equal to beta times V0 delta T. Delta V is the change in volume of the object, V0 is the initial volume, delta T is the temperature change of the object, and beta is the volumetric expansion coefficient for the object. Just like the linear expansion coefficient, the volumetric expansion coefficient will vary for different materials. It can be higher or lower, or negative or zero. And the same principles for the linear expansion coefficient apply to the volumetric expansion coefficient. Here are some sample volumetric expansion coefficients for selected materials, and it's important to know that most gases have a volumetric expansion coefficient of 3.4 times 10 to the negative 3 inverse Kelvin, and this can be calculated using the ideal gas law. Another important thing to note is that for isotropic solids, meaning solids that are the same all the way through, beta is equal to 3 times alpha, and this is because volumetric expansion occurs in 3 dimensions, whereas linear expansion only occurs in 1 dimension of measurement. Now we're going to go over an example problem. So suppose we had a 5 meter cubed bucket and we fill that to the rim with gasoline, and then we heat up the gasoline by 20 degrees Celsius. How much gasoline will end up spilling out of the bucket? Well, since we're talking about volumes, we need to bring up the formula for volumetric thermal expansion. Delta V equals beta V0 delta T. Now we know that the initial volume of the gasoline is 5 meters cubed. We know that the change in temperature is going to be 20 degrees Celsius, or 20 Kelvin. And we can find beta, which is the volumetric expansion coefficient, and that is equal to 9.5 times 10 to the negative 4th inverse Kelvin for gasoline. Now, if we plug all of these values into the equation, we'll get that delta V is equal to 0.095 meters cubed. But this is just the change in volume. If we want to know the final volume of the gasoline, we'll have to add the change in volume to the original volume, and if we do that, we'll get 5 plus 0.095, which is 5.095 meters cubed, and that's the final volume of the gasoline. Now, if we know that's the final volume of gasoline, and we know that the bucket can only hold 5 meters cubed, then the amount of gasoline that will spill out of the bucket is 0.095 meters cubed, which is the answer. Now let's go over another example problem. Oftentimes when a teacher wants to explain thermal expansion to students, they'll use a setup with a ball and a metal ring. They'll try to pass the ball through the ring, but it won't work because the ring is too small. Then they'll heat up the ring and try to pass the ball through again, and this time it'll work because the ring has expanded. Suppose a ring made of stainless steel has a hole with a 1.5 centimeter diameter at room temperature, or 300 Kelvin. How hot must the ring be so that a 1.55 centimeter metal ball will pass through it? Well, now since we're talking about linear distances and diameters, we're going to have to use the formula for linear expansion. And this is the equation. Now we know that the diameter of the ring, in order for the ball to be able to pass through, is equal to the diameter of the ball, 1.55 centimeters. And we know that the initial value for the diameter of the ring is only 1.5 centimeters. Also look up the linear expansion coefficient for stainless steel, which is 5.19 times 10 to the negative 5 inverse Kelvin. Plugging all of these values into the equation, we can find that delta T is equal to 642 Kelvin, meaning that the final temperature is equal to the initial temperature, which was room temperature 300 Kelvin, plus 642 Kelvin, which is equal to 942 Kelvin, which is the final answer. So now that we've gone over a couple example problems and we figured out how linear and volumetric thermal expansion works, that's all for today. I hope you've learned something from this video, and as always, the more you know, the better you are.